Okay, let's continue with our studies in multipole expansion. Um, in the last class, we have seen some of the definition of multipole moment, and one of the critical point to notice is that the multipole moments depend on the coordinate system. So we have also looked at the Cartesian moments, and let's try to understand the multipole moments in the spherical polar coordinate and how they are different from the Cartesian coordinate system, and whether we can make any physical connection with that. The linear moment and conservation of them are natural for the Cartesian coordinate system, and hence the Cartesian multipole moments too. So, however, in analogy, in the polar coordinate, we have angular momentum and torque, uh, which are playing important role, which we have seen in the dynamical system, simple Newtonian mechanics, or in the extended body, study of extended body. The torque or angular momentum produced by an extended object on a point particle, since the angular momentum lives on the sphere, we'll have a multipole also living on the sphere. Of course, the angular momentum is a bit of a sticky matter because of the same problem that they have commutation relation between them. In the case of Cartesian moment, we have not used Laplace or Poisson equation, and the symmetry or physics corresponding to those have been not exploited properly. Irrespective of that, we have obtained whatever charge symmetry of the charge would reflect in the symmetry of the multipole moment. However, since the Laplace equation is separable in polar coordinate system, radial part is completely separated from the angular part. Radial part can be written as r power n, and the angular part can be written as ylm. This natural separation results in the interesting way that there is a natural way of expressing multipole momentum of ylm for each L, because the radial function is completely separated, and for a given r we can have a ylm. So that is the basis of defining the uh, polar spherical polar multipole moment. So let's quickly recall the definition of multipole moments in the spherical coordinate, which we have been done earlier. So YLMs are used for defining them as a QLM. They comes as given in these equation. You have to note that the R power uh, L for LM, that is a similar concept is present in the Cartesian system too, and in principle we have complex quantity because of YLMs are complex. So once we have this multipole moment, one can define all the expansion for the potential, and we have seen that the potential itself is defined, and that is where you get the idea that ALM is defined as multiple moments. And of course, you have YLMs in the case of potential and the radial dependency, and this uh, vicious snake with the eyesight. Of course, let's have some more understanding of angular momentum, or restate what we have learned in the quantum mechanics. Classical mechanics usually ignore this factor, whereas in quantum mechanics it plays a very important role as a commutation properties of angular momentum. We have following commutation property of uh, angular momentum components. Lx into Lxy would be commutation will be expressed in terms of Lz, and all other in the cyclic order. So if you are talking about the classical system, you could replace the commutation relation by the Poisson bracket, which you would get a similar result. The main idea here is that angular momentum being a vector requires a three component. However, since it is living on r is equal to constant surface of the sphere, uh, any two variables or scalars should be sufficient in terms of r, theta and phi to describe completely the angular momentum. However, if you have a vector, there will be three components, and these components were related with this commutation relation. This makes it a problem little more complicated, as if you want to choose an independent component of angular momentum, we have seen in the quantum mechanics, it says in the good quantum numbers. One of the good quantum number is a LZ, which is taken as easily translatable from Cartesian to polar coordinate. Other thing is that often when we have a actually symmetric or azimuthally symmetric system, then LZ is conserved. So that's why LZ is one of the better quantum numbers, and the other quantum number is L square. We don't take Lx or Ly. So in the similar spirit, in the quantum mechanics, often L plus and L minus is defined with the following manner. So we also have, they are related to L square, so that they could be also chosen as a independent or good quantum number. One of them, you can see that the other is a complex conjugate of them. So that is the basic idea we have about the commutation relation and independent components of angular momentum. Let's look at the multipole moments. Multipole moments are coefficients of YLMs when you express the potential. So you can have a complex uh, one or the complex conjugate depending on the YLM, the variable used. You have rho, the density, and r power L. So that is in the similar spirit of the various moments defined in the Cartesian system. L is directly related to r power L, that is, we have seen higher moment should be related to r power n. So for a given L, we have various components of M, which goes from minus L to M, that also we have seen in the expansion of spherical harmonic. So when L is equal to 0, we call it a spherically symmetric or the monopole moment or the single point charge, effective single point charge. When L is equal to 1, we have a dipole. In this case, we have three values of m's, minus 1, 0, and plus 1. However, you see that there is a relation between the YLM, YALM, and YL minus m in terms of their complex conjugate. So that makes it only two of them are independent. Together, we get all the required quantities and so on. So the next one is a quadrupole moment where L is equal to 2. So we have here a set of 5 m's from minus 1 to plus 1. Again, there is a relation between them, which makes them only 3 of them are independent, and then that is you can express with each other depending on the properties and so on. So that is how you define the quadrupole. You can also have a higher multipole, but often their significance is not so much because when L is larger, R power, we have seen that they fall off very rapidly. And here let's look at the individual moments and try to connect them with the Cartesian moment. Let's take a first look at the multipole moment, monopole term. L is equal to 0, M is equal to 0. The simplest case, we have a complete integral of density, and that is the total charge in the system. So there is no angular dependency in this case because all the charges are concentrated at the center, they would act like a single point charge or spherical charge distribution. There is no angular dependency, and potential goes as simply Q by R. So that is a usual Coulomb potential. So you have a density given inside some region. When a far off observer sees it as simply a point charge, and the system is spherically symmetric. At this stage, there is no difference between the Cartesian and polar multipole moment because it's just a point charge. There is nothing else depends on it. So higher moments will have a difference, and they will be moving away from the spherical symmetry, not because of the Coulomb force, it's because of the density distribution itself is not spherically symmetric. Let's start with the dipole term. So we have a definition of dipole. It's R into rho. Of course, we have YLM, which is not present in the case of spherical Cartesian system. Of course, you can put y 10, which is cos theta. But if you look at this, r cos theta is actually z component. So we can put it in terms of simplify in terms of pz, z component of a Cartesian moment, which is we have defined earlier, and which would look like a simple dipole. So that is what we expect in this case when you have a z component, which would be completely a real because of YLM is completely real. So we have Q star 10 or Q10 is directly. So this is very similar to the idea of z component of angular momentum, and we have more detailed look on it on the different perspective. I've been spending a lot of time making these movies, and you can have a look at them. Of course, let's go on with more dipoles. Let's compute next one, that is a Q11 star. So again, these terms are same because of the dipole moment, except that the basis function of YLM have changed. So now you see that they have a little bit more complicated expression putting Y11 spherical harmonics. But again, we can identify some of the known things. We know that this is the x prime coordinate. Similarly, we can look at this quantity, and that is y prime, and this is x prime, and then we can combine them, and we get a expression in terms of the px and ipy. So this is all look at how we have related to the x and y component of linear multipole moments. So that of course px and py are defined here. So this is in analogy with the angular momentum. You see that it is not convenient to have a px or py. It's a combination of which is important, and that is what it is reflected because of the we are using the geometry which is suited for our physics, that is this thing. So of course other component we can calculate, we don't have to actually do it because of the symmetry, and you would see that this is px plus ipy, which is very similar to the L plus component of the angular momentum. This is how the Cartesian linear moments are converted into the meaningful angular momentum, and then we can see that we can use Q11 and Q10 are used to describe the dipole moments similar to angular momentum and the square of them. This is the geometry of absolute square of them. We have seen that that is what it matters, and it looks like a it doesn't look like anything like a dipole which we have seen. It looks like a more like a torus. So that is why we call it a toroidal dipole field. We'll come to more of this later and with the examples. Let's stop now, and we'll continue with the quadrupole moment in the next video. Oh, and